Welcome back. Today we open up an SDH frame and ask a very practical question. How much of it actually carries user data, and how much is wasted on framing overhead? We are looking at an STM-1 frame, the basic unit of synchronous digital hierarchy transmission. We are filling its payload area with ATM cells, the 53-byte fixed cells used in early broadband networks. Each cell has 5 bytes of ATM header, 1 byte of adaptation overhead, and 47 bytes of actual user data. 4 questions. Part A. How many complete ATM cells fit inside one STM-1 frame? Part B. How many bits of actual user data does that give us per frame? Part C. What percentage of the total STM-1 capacity is genuine user data? Part D. At what data rate is the user information being transmitted in megabits per second? First, the frame. An STM-1 frame is a two-dimensional grid, 9 rows by 270 columns of bytes, that is 2,430 bytes per frame, and at 8 bits per byte, exactly 19,440 bits per frame. Now the layout. The first 9 columns of every row carry section overhead. 3 rows are RSOH, regenerator section overhead. 1 row is the AU pointer. 5 rows are MSOH, multiplexer section overhead. These 9 columns of overhead times 9 rows give us 81 bytes of section overhead, framing, error monitoring, pointer adjustments, and management channels. The remaining 261 columns are the payload area, but 3 of those columns are reserved for path overhead, the POH, tracking the user signal as it walks across the network. 261 minus 3 equals 258 columns of usable space across all 9 rows. 258 times 9 equals 2,322 bytes. This is what we have to fill with our ATM cells. STM-1 is transmitted at exactly 8,000 frames per second, so each frame lasts 1 over 8,000 seconds or 125 microseconds. That is the heartbeat of STH. Now the cell. Asynchronous transfer mode, or ATM, was the technology of choice for broadband transport in the 1990s. It uses fixed-size cells of 53 bytes, chosen as a compromise between voice latency and data efficiency. 5 bytes are the ATM header, routing, traffic class, error check. 48 bytes are the ATM payload. Of those 48, 1 byte is the adaptation layer header, AAL, leaving exactly 47 bytes carrying actual end-user information. So per cell, 53 bytes shipped, but only 47 bytes of user data inside. The cell-level efficiency is 47 over 53, about 88.7%, already an 11% overhead just at the cell level. Now we will see how this combines with the frame overhead. Part A. How many cells fit in the payload? We have 2,322 bytes of payload area in one STM-1 frame. Each cell is 53 bytes. 2,322 divided by 53 equals 43.81. But cells are atomic. We cannot cut one in half. SDH allows cells to span 2 consecutive rows of the payload, so we just round down to the integer that fits. 43 complete cells per frame. Total bytes occupied. 43 times 53 equals 2,279 bytes. The remaining 43 bytes of the payload sit unused, waiting for the next frame to start a new cell. Part B. Actual user data per frame. Each cell carries 47 bytes of user data. 47 bytes times 8 bits per byte equals 376 user bits per cell. 43 cells per frame times 376 bits per cell. That is 16,168 bits of actual user information per frame. Part C. Efficiency. What fraction of the total STM-1 capacity is genuine user data? 16,168 user bits divided by 19,440 total bits equals 0.8317, or about 83.17%. Just over 83% of every byte that crosses the link is user data. The other 17% goes to framing overhead, headers, and the unused tail of the payload. Part D. Data rate. Each frame is transmitted in 125 microseconds. User data per frame is 16,168 bits. Data rate equals 16,168 bits divided by 125 microseconds, which is 129.344 megabits per second. Compare that to the line rate of STM-1, 155.52 megabits per second. We push 155 megabits of bits down the wire, but only 129 megabits is real user information. The rest is overhead, doing the work of keeping the network synchronized and addressable. 3 takeaways from this exercise. 1. Framing overhead is a tax. Every protocol layer adds bytes that the user does not see. SDH spends about 3% on the framing structure, ATM spends about 11% on cell headers, and the unused tail of the payload eats another % or 2. Add it all up and roughly 17% of the bandwidth never reaches the user. 2. Small fixed cells trade efficiency for predictability. ATM chose 53 bytes because tiny cells keep voice latency low. Any individual call cannot be held up by a giant data packet sharing the link. But that small size means a relatively large header-to-payload ratio. 3. In the next 2 videos, we will run exactly this calculation with 2 different payload schemes. 576-byte IP packets, where we will see efficiency collapse, and a mixed packet size that shows what happens when you mix cells of different sizes in the same frame. The STM-1 frame stays the same, only the way we fill it changes, and the answer changes dramatically with the payload choice.